This video is about implicit functions. Those are functions where some dependent variables depend on other independent variables. And we consider an application of this in thermodynamics. Namely, we consider the equations of state. They determine the relations between some quantities like the pressure, entropy, internal energy, the volume and temperature. Now, suppose that for a certain gas, we are given the following equations of state. Namely, the pressure is some function of the volume and temperature, and this function is called F. For the entropy, we have the same, but we have a function G, and for the internal energy, we have some function H. And we assume that these functions F, G, and H are known. Now we want to find an expression for delta U, delta P, where we keep S constant. So you want to know the change in the internal energy if the pressure changes when we keep the total entropy constant. Now this is a problem from the article by Kustush, so for those of you who are interested, you can read this. Now these functions F, G, and H are a little bit vague for now, so let's see what kind of functions they use in the article for this. So they use for the pressure, P is N times K times T divided by V minus N times B minus AN squared over V squared. And in this function, N is the number of particles that we have, which is a constant in this case. A and B are some coefficients, and this K is the Boltzmann constant. So we see that this indeed is some function of the volume and the temperature. Well, for the entropy, we have something similar. We have the following expression, N times K times the logarithm of V minus NB T to the power 3 over 2 divided by N times phi plus 5 over 2. And here we again have the constants N, K, and B. And we also have phi, which is the residual entropy, which is also a constant. So this is a function G of the volume and the temperature. And then last we have U, the internal energy. This is 3 over 2 times N times K times T minus A N squared over V. And we see that this is also some function H of the volume and the temperature. Now in this video we will consider the general case, so we will keep F, G, and H some general functions. Now we will determine the partial derivative of U with respect to P, where we keep S constant. And we do this by following the steps from the lecture slides. So the first step will be identifying the dependent and the independent variables. And as we can see in the question, we have 5 variables that we consider. And together with these 5 variables, we have 3 equations that are given. So that means that we have 5 minus 3 is equal to 2 independent variables and 3, so 5 minus 2, dependent variables. Because the number of dependent variables is equal to the number of equations that we are given, and the number of independent variables is the number of total variables minus the number of equations that we are given. And if we look at the expression that we want to determine in this question, so we want to determine delta U, delta P, where we keep S constant, it seems like a logical choice to choose P and S as our independent variables. So P and S are independent variables. And then our dependent variables will be U, V, and T. Now step 2 will be to differentiate the equations that we have using the chain rule. Using the chain rule. And we start by finding a first expression for this delta U, delta P, where we keep S constant. And we use the third equation for that. So we know that U is equal to H, V, and T. And we rewrite this in a form that we can recognize. And since P and S are our independent variables, we know that the variables u, v, and t will depend on P and S. So we define a function capital H, which depends on u, which depends on P and S, v, which depends on P and S, and t, which depends on P and S. And this function capital H is equal to u, which depends on P and S, minus this h, which depends on v, depends on P and S, and t, which depends also on P and S. And we know that this must be equal to 0, since u is equal to this function little h. Now, if we take the derivative of this capital H with respect to p, where we keep s constant, then if we use the chain rule, we get delta u, delta p, where we keep s constant, and here we recognize the term that we want to determine, minus, and now we use the chain rule, so we get h of v, and then delta v, delta p, minus h of t, delta p, delta p, and this is equal to 0. Now we can rewrite this a little bit to see that delta u, delta p, where we keep s constant, is equal to hv, delta v, delta p, plus ht, delta t, delta p. So this is the first expression that we find for delta u, delta p, where we keep s constant. And if we look at this expression, then we see that we can determine this hv and this ht, because our function h, we assume, is known. But we need to determine an expression for delta v, delta p, and delta t, delta p, because these two are still unknown. Now, and to do that, we will use the other two equations, namely p is equal to f and s is equal to g. And we will do something similar that we did for u. So we first write these two equations in a form that we can recognize. So we have a function capital F, which depends on p, v, which depends on p and s, and t, which depends on p and s. And this is equal to p minus f, which depends on v, depends on p and s, and t, which depends on p and s. And this is equal to 0. This is our first equation. And for s, we do something similar. So we have our function g, which depends on s, which also depends on v, on p and s, t depends on p and s, is equal to s minus little g, which depends on v, depends on p and s, and t, which also depends on p and s. And this is also equal to 0. So this is our second equation. Now, and we will use these two equations to determine an expression for this delta v, delta p, and delta t, delta p. So we will differentiate these two equations with respect to p using the chain rule. So we see that we get delta f, delta p, where we keep s constant, is equal to dp dp minus fv, delta v, delta p, minus ft, delta t, delta p is equal to 0. Now we can simplify this a little bit because we know that this dp dp is equal to 1. And for the second equation, we get delta g, delta p, where we keep s constant, is equal to, well, delta s, delta p is equal to 0 because we keep s constant. So we get a 0 over here, minus gv, delta v, delta p, minus gt, delta t, delta p is also equal to 0. Now we will use these two equations to first find an expression for delta t, delta p. And we will do some tricks to get rid of these terms over here. So let's first write out again what we have. So we know that 1 minus fv, delta v, delta p, minus ft, delta t, delta p is equal to 0. And that minus gv, delta v, delta p, minus gt, delta t, delta p is equal to 0. Now, and we note that if we multiply the first equation with gv everywhere, and the second equation with fv everywhere, and we subtract 2, that these two terms will cancel out. So let's do that. So we multiply the first equation with gv everywhere, and the second equation with fv everywhere. And then we subtract the 2. So if you do that, we get a gv over here. Well, these two terms will cancel out, like we said. So we get gv, and over here we get minus gv ft plus fv gt times delta t delta p, and this is equal to 0. Now we can rewrite this, and if we do that, we find that delta t delta p is equal to gv divided by gv ft minus fv gt. So now we have found an expression for delta t delta p. And notice that this expression involves the Jacobian of g and f with respect to the variables v and t over here. And we will do something similar to find an expression for delta v delta p. So let's again first write out the first two equations that we had. So we had 1 minus fv delta v delta p minus ft delta t delta p equal to 0, and minus gv delta v delta p minus gt delta t delta p is equal to 0. So now we want to get rid of these terms over here. And if we multiply the first equation with gt everywhere and the second equation with ft everywhere, then we see that these two terms will cancel out. So let's multiply the first equation with gt everywhere and the second equation with ft everywhere. And then again we subtract 2. So that gives us over here gt, then we get minus gt fv minus ft gv times delta v delta p, and these terms with delta t delta p will cancel out, so this is equal to 0. Now we can rewrite this, and then we get delta v delta p is equal to gt divided by gt times fv minus ft times gv. So now we also found an expression for delta v delta p. And we know that we again get a Jacobian term of our vectors f and g with respect to the variables v and t over here. Now, if we go back to the expression for delta u delta p that we determined in the beginning over here, then we see that we now know everything that we need to know. So let's write this expression out explicitly. So we have delta u delta p, where we keep s constant, is equal to hv delta v delta p plus ht delta t delta p. And now we can fill in the expressions that we found for delta v delta p and delta t delta p. And if we do that, we get h of v times gt divided by gt fv minus ft gv plus ht times gv divided by gv times ft minus fv gt. And we can put everything together into one fraction. And if we do that, we get hv times gt minus ht times gv divided by fv gt minus ft gv. So this is the final expression that we find for delta u delta p, where we keep s constant. And finally, we notice that in the numerator we get the Jacobian of our functions h and g with respect to the variables v and t, and in the denominator we get the Jacobian of f and g with respect to the variables v and t. Now, and if we look back at the expressions that we had in the beginning of our functions f, g, and h, so that were those expressions, then we can get a more clear expression for this delta u delta p over here. So to get this expression, we first need to calculate some derivatives. Now you can calculate those expressions for yourself, so I'll just give the final results here. So we have fv, the derivative of f with respect to v, will be 2 times n squared times a divided by v to the power 3 minus nkt divided by v minus nb squared. And the expression for ft will be n times k divided by v minus n times b. Now for g, we have gv is equal to n times k divided by v minus n times b. And for gt, we find 3 times n k divided by 2 times t. And then the final two derivatives will be h of v, and this is n squared times a divided by v squared, and h of t is 3nk divided by 2. Now, we can put all those derivatives together into the expression that we found over here. And if we do that, then we can define some functions. So let c be equal to v minus n times b times t to the power 3 over 2. We have alpha is equal to minus 5 over 3 times n k c to the power 2 over 3 divided by v minus n b to the power 5 over 3 plus 2a n squared divided by v to the power 3. And we have beta is equal to minus n times k c to the power 2 over 3 divided by v minus n b to the power 5 over 3 plus a n squared divided by v squared. And if we use these two over here, then we get delta u, delta p, where we keep s constant, is equal to beta divided by alpha.